All right, if you would please take out your MT StatPal booklets and turn to page 37 for the central limit theorem for means activity for today. So today is a really important activity because what we're doing is we're connecting things that we have learned about distributions like uniform, normal, and skewed distributions, and we're going to see what happens when we look at the average from those distributions, and then we're going to say, what does that change when I look at the distribution of the averages? And it turns out that that's what we're going to be looking at, things like that, for the rest of the semester. We need this transition from probability so we can do statistical inference. Okay? So if you would, I would like to see what you remember about distributions and what you know on the first page with problem number 1. And so if you would quickly try to actually sort of match those histograms with their descriptions, then we'll check that really quickly. So let's see, I'm going to randomly call on some students, and let's start with Evgeny. Could you please tell me what you think number A is? The picture that is like a big black box. Uniform, very nice. And let's see who's next on the random calling. Brianna, how about B? Skewed, and it is skewed to the right. And then finally C, Alexis. Normal distribution, very nice. What did you notice about their means? Just take a moment, look at their means, look at their medians, and look at their standard deviations. All right, those are going to be important because we're going to work with each one of those individually. So on the next page, please, number 2, we look at 3 different pictures, 3 separate images, and I'm going to give you a minute to see if you can answer the questions below that help you understand an original graph, what happens in a sample, and then what happens to the sample means. Okay, so take a moment and then we'll answer the questions together for this first distribution. Okay, so let's see if we can actually regenerate the original distribution right here. So in StatCrunch, which you have access to through my Stat Lab, then we have StatCrunch, and it will actually have these applets that you can go back and check. And it says, let's look at a sampling distribution. So we're going to learn about distributions of samples. And the first one we want to look at is if the original population is uniform. Now, can you look in the picture, please, Ben, and tell me what the lower bound and the upper bound are for the distribution that we have?
The lower bound is 0, the upper bound is 10.
All right. And it is uniform, and so we want to see if there's anything else we need. I think that's enough. We can compute. And so the first thing it does right here is give us a picture of a uniform distribution for that ranges from 0 to 10. And Lawrence, when we talk about a uniform distribution, what does that tell you about how likely each value between 0 and 10 is to occur? Yeah, so each value between 0 and 10 in a uniform distribution.
They all have like equal chance of occurring.
That's very nice. They all have equal chance of occurring. So I'm going to start with a sample of size 2, just like is in your book. And let's have it take a sample from here of size 2, where each value from 0 to 10 is equally likely to occur. Okay, so one time first. There they are. They're the 2 values. So the first thing it did was drop down 2 values that are equally likely between 0 and 10, and it found the average in this next picture. Well, that was pretty good that showed up here, right? Because the average in this particular one of these 2 values turned out to be 5.5, which was pretty close to the original one, right? Okay. So, what do you think would happen if I drew another sample of size 2 from the original distribution? In other words, what would be a reasonable estimate for the average of the next time I do this?
5.4.
Yeah, so in the similar, very similar values, let's see. Let's draw one more. Oh, right in the middle. Let's do another one. And another one. And another one. How many times? Oh, okay, I've done it 5 times. Okay, so I've generated 5 different samples so far. So take a moment, talk to your neighbor, and actually talk to your neighbor, and see what you think is going to happen if I continue this process, let's say, basically 1,000 times. Okay, so talk to your neighbor for just a second, and then we'll do it.
It's going to get more because after a while you'll keep getting weeds. They'll keep shooting up through the middle, and from that you'll get down one time down the other. So.
Isn't it something about the rule of what is the thing that's like the rule of our numbers for like the more numbers you use, the more narrow.
Yeah, you have more repetitions, so therefore it's going to get closer.
So I'm going to keep the sample sizes 2, but because each of these are equally likely, it's not exactly the law of large numbers. It's actually going to have a name, and that name's going to be the central limit theorem. See, so I heard some really good conversation. In fact, Alexis, could you repeat what you just said slightly? I mean, just the short version of it.
It'll become more narrow.
And if you're not looking at her, her hands are indicating that she believes it's going to be bell-shaped kind of curve, mound-shaped and symmetrical. Well, let's see. So let me just do it 1,000 times. Well, there it is. So that was really fast. So this is really important to describe what this picture is showing. And so take a moment and see if you actually know what this picture is showing. Okay, so think for yourself first and see if you know what this picture is showing. Okay, April. What do you think that the picture with the histogram with the green of the sample means? What is that showing for us? It is the average of the samples when they were size 2 from a uniform distribution. Very nice. Okay. And so when Alexis was telling us with her hands that it was going like this, she was absolutely right. That it was much less likely to be in the tails and that they flattened out and it was clustered in the center because it, quote, averages out, right? All right. So now, if we look this time on question number 4, take a minute. It shows you 2 pictures of the original distribution in question 4. And take a minute and see what's going to happen if the original distribution is skewed. So I'll show that up here for just a second as well. Sample distributions where the original one is skewed to the right. And for that one, yes, but I continuous because I think I need to, let's see if that's enough. Oh, I may not get the exact same picture I want. Yes, I did. Okay, great. So there's the picture, the same one you have in your book. It only shows 2 of the 3, and you're supposed to draw this one yourself this time. Okay, so take a moment and let's see what you think is going to happen. Have Alyssa describe tell what your group said, please.
We said that for 1,000 sample means it's going to be the same shape with the right skewed, but it's going to be more narrow and condensed.
Okay.
And so there's more samples. It's kind of like a bigger graph.
Okay. So Lawrence helped us. We'll stay with that for just a second because I want the why behind it. I think you've done a really nice job of describing it. Lawrence helped us last time to think about what kind of results we would get when we sample from a uniform distribution. What do we think is most likely if we're sampling from a distribution that's skewed right? What outcomes would be most likely here? Shannon, you want to try that?
Would it be a lot of the
Yeah, so values from the high side of the skew, it's a good description of it, are going to be more likely than those in the tail. That's right. So let's see what happens when we actually simulate that. We'll start with 1 time again. And then we'll do that again. Oh, so we got 1. So each time we've been sure to get 1 from the high side and then the lower side's coming. But the average is moving down here, not in the center like it was on the uniform. So, and then that keeps going and keeps building up. So now let's just do that 1,000 more times and see if that matches roughly what you drew. So we still have a long tail. We are clustered here. The mean and the median are not in the same spot in the same way that it was in the uniform, which is not surprising because they're different up here as well. All right. So Alexandra, do you think that you could describe what the green graph of the sample means is on the bottom here?
The sample means of 1,000 samples of size 2 of a skewed right distribution.
The sample means, and that's the key part. So this is the averages. When we drew samples of size 2 from a distribution that was skewed right, and we did that 1,000. Actually, this time I did it 1,007 times, but it's, in your book it was 1,000 times. That's right. And it also is skewed to the right. So the original distribution that we did first was uniform and it became normal. This one was skewed right, but it stayed skewed right. But we're using right now sample sizes that are really small with 2. So let's look one step further. And if you would, turn the page and look at problem number, we're up to problem number 7. The original distribution is normal. And then in this one, it goes straight to the picture of the sample means, and it just asks you to compare the basic shapes and the means of them. Okay? So if you'll do that for a second and talk to your neighbors, I'm going to get the picture up here and we'll look at the simulation. All right, thank you. Let's pull back together for just a second on this. And I heard conversation that said that, hey, the mean is about 123. So let's see if that happens when I do that 1 time. Oh, it was a little higher. 2 times. Now it's balancing out, getting lower. And if I continue that 1,000 times, then the mean is very close to 123, in fact. So here, what we're looking at is with a sample of size 2, this distribution of the averages of those samples of size 2, and this would be the distribution of that. So what was the one thing that was the same each time, approximately the same, each time we did samples of size 2? Was it the shape or was it the center? The center was approximately the same every time, no matter what the original shape was. Well, now we want to see what happens if we take larger sample sizes. So let's go back to the uniform distribution. And let's get that generated again from the start. And this time, though, I would like to take a sample of size 20 instead of 2. And all I have to do is just tell it, not 200, sorry, 20. All right. So think for a moment before we see anything and make a hypothesis about what you think is going to happen. What's going to happen up here when I tell it to draw 20 samples? And then what's going to happen down here on the next one? Kelsey, what do you think is going to happen when I draw 20 samples from this original distribution?
You're going to have a point for each of the random sample of the 20.
Very nice. Do you think they're going to all be clustered here or clustered in the center or clustered on the side?
No, they're pretty much going to be spread out.
Because what kind of distribution is this?
A uniform.
And that means each data point is equally likely. So let's draw those. 1 time. There's the 20 that I got this time. And then what's this picture showing me? Everyone can answer. The sample mean of those 20. That's exactly right. Very nice. So let me do it again. Is the second line going to look exactly the same when I do it the second time?
No.
But the average was similar, right? Yes, I didn't set my bounds on this one like I did before, 0 to 10, did I? Should have done that. Let me do that. So we match what you have. So sampling distribution, 0 to 10. Compute. One time, there it is. And then another time, and another time, and another time. So they're all centered around what number? Hey, what's different this time than when we did this with a sample of size 2?
Well, from that, because the sample size increases, standard deviations.
So Lawrence, could you say that again?
Because the sample size is increasing, the standard deviation is going down.
Yeah, so, but can we figure out why? What's happening? We're taking what down here? What's this a picture of? The average, the sample mean, and what's happening with those 20? These are canceling out, and these are canceling out, and these are canceling out, and you're ending up,
They're forming into normal curves.
yeah, in the center. So let's give 1,000 this time. So just like before, we got a mound-shaped distribution. It's a little smoother this time. But the biggest change is, as the sample size increased to 20,
Standard deviations.
those sample means fell into a narrower range. That was hard to say, but that's correct. But that spread, what term do we use for it and care about to use for it most? For spread. Standard deviation, that's what we use most. And so the standard deviation is smaller. Very nice. All right, so then if you would, on page 42, you have a nice big grid. And on this grid, we get to practice matching original population distributions across the top with the sample distributions of size 2 and then sample distributions of size 20. And in this case, they actually are lined up for you. So this is the uniform, and then it's sampling distribution of sample means when it's size 2, sampling distribution of sample means when size 20. Then the next column is for the skewed data, and the last column is for the normal data. So take a look at it and see if you can draw conclusions from it. All right. Okay, so now I'm going to randomly call on you again to state the conclusions that your group came up with for this chart, okay? So let me look at my random calling. There we go. Alex, you're next. Alex, can you tell me from the table what you concluded about the mean, just the averages of each of the distributions, that means the original population distributions, compared with their sampling distributions?
The more times the average is taken, the more specific the data became.
The average is taken, the more specific the data became, okay? Let's see, Desiree, could you add to that, please?
The more samples that they had, the smaller the curve got.
Okay. So let's see, Abigail, what did you find out just about the means? I'm getting lots of great information, but I'm looking for information just about the averages. So if I look at the average of the uniform, and then I look at its average when it's the sample distribution of size 2, and then the average when the sample distribution is size 20, and then I do the same thing for each of the distributions, what did you observe?
They stay generally the same.
Yes, so did anyone else notice that? Yeah, so what can we say is true? Let's see, sorry. The other Abigail, so we got one Abigail, so the other Abigail, what can you say, would you restate or say what you found to be true about the distribution, about the averages of the distributions of the sampling distributions compared with their original populations?
That they stay the same.
Yes, and it turns out that what you are coming up with right at this very moment, let me put the screen up, is the central limit theorem, okay? And you have just given me the very first part of the central limit theorem. The mean of the sample averages is the same as, you said they stay the same as the population mean. Okay? So the average of those sample means is the same as the average of the original population. So that's one of the key things that we want to come up with, and you just came up with it by yourselves. And actually, some of these were actually already described by the first students who were called on for this, but let's repeat it anyway. What would we say when we have larger sample sizes? So this is the second one. For larger sample sizes, what can we conclude about the basic shape of the histogram? And so my next random person is Mark. Mark, what did you conclude, you and your group, when you have larger sample sizes? So which row of information are we looking at here? The bottom one for the larger sample sizes, just about the basic shape of the histogram.
Well, the larger the sample size gets, the more bell-shaped and narrow it becomes.
So you're answering two things for me at once, and so I'll take that first one, which says for larger sample sizes, now I believe he used the word it in there, and I'll have to make sure I know what that is. For larger sample sizes, the basic shape of what? Do you want to tell me, or do you want one of your group mates to tell me?
The basic shape of the histogram.
The histogram of what? Yes?
Of sample means.
Yes, the basic shape of the distribution of sample means is approximately normal. We already know that word, but you use the term bell-shaped. Sorry, I'm writing normal. Bell-shaped, mound-shaped, and symmetrical. Any of those? Very good. Yeah. All right. And now, two people have already answered the third one. And both times, and for both of these other questions, you just could not resist answering the third question, which says that when you compare sample sizes of 2 and 20, what can you say about the spread or the variability of the sample means distribution, the distribution of the sample means? So let me get the random calling for this, and that would be, okay, go ahead. Very nice. So for larger sample sizes, as the sample size increases, the spread of the distribution of sample means is smaller than the spread of the original distribution. Congratulations. You just came up with almost all of the information for the central limit theorem all by yourself. One of the most important theorems, the central limit theorem, it's the only theorem we do this whole semester, and you just did it all by yourself. 3 things. Now, there's a tiny piece of information that you could not expect to come up with yourself, and that is actually this relationship between the spread of the distribution of sample means and the spread of the original distribution. And if you turn the page, or just look on the next page, which is 43, it states in the simplest of terms that we sort of can, the central limit theorem. You're going to need to know that. You can expect it to be on your test, but mostly you're going to use it over and over again, even though we won't say that that's what we're doing every time. So actually, Kane, would you be willing to read the central limit theorem for us?
Just that one sentence there?
And then the 3 bullets.
Okay. If the sample size n is large, then the distribution of the sample mean is normal or bell-shaped with the mean and with the standard deviation.
So with mean mu, which is the original population mean, and a standard deviation of sigma over the square root of n. So we can turn the central limit theorem, CLT, for central limit theorem, which is spelled out in detail here, and it will tell us that the distribution of the sample means has mean equal to mu. Well, that's a lot of symbols there. So the distribution of the sample mean has mean of the sample means equals original population mean, and standard deviation of those x bars, and this is the one that'll be tricky, is sigma over the square root of n. Okay? So the standard deviation of the sample mean is the original population standard deviation over the square root of the sample size. And turns out those are true regardless of the sample size. If n is large, the distribution of the sample means is approximately normal. And we're going to use that today, in fact, in just a few minutes, as we apply that to statistical inference and as we learn about something called confidence intervals. We're going to need that. And when we do hypothesis testing, we're going to need that. So we keep needing that. Okay? Questions? Okay, we'll take just a moment and re-say those things to yourself to make them stick, right? It's one thing to do it, you've done it, you've seen it, you've talked about it, but now you need to go one extra step and make them really stick in your mind. And then we'll practice some problems with it too.